Yeah, welcome to the last day. Unfortunately, we cannot do it in person. The government showed a lot of precautions about the typhoon. But we are very happy to have Professor Emil Martinec from Chicago University to tell us about black hole S matrix engaged gravity duality. Okay.
Okay, so are you seeing my screen now? I see a gallery. What am I doing?
Yeah. I can see your iPad.
You can see my iPad. Okay,
Yeah.
good.
Mhm.
Um, so, well, thanks, Pei Ming, uh, and other organizers for the opportunity to visit Taiwan. It's my first time here. So, I see you pulled out all the stops to entertain us, this week. Um, Uh, yeah, I would make a joke about feeling under the weather, but I think when the weather is a super typhoon, it's probably not allowed. Um, anyway, um, what I'm going to talk about today is some kind of an evolution in my thinking about um, a black hole information problem in string theory. Um, and uh, so I thought I would begin, since not everybody in the audience is a string theorist, and following in Samir's footsteps of trying to be as pedagogical as possible, that I would just present a bit of a general overview of gauge gravity duality in string theory, and then move on to the specific topic uh, that I would like to discuss. So, what is gauge gravity duality in string theory? Well, it basically arose, when soon after string theory was discovered to be not just strings, but have a variety of other extended objects in it, in particular D-branes. That one could study a situation where one had a collection of D-branes in string theory. So what's a D-brane? D-brane is just some extended object, um, where when you have a collection of them, uh, the dynamics is governed by open strings, which stretch between the branes. Um, and so if I have n such branes, then the low energy dynamics on those n branes is some un supersymmetric Yang-Mills theory. Okay. On the other hand, these are some heavy objects. They have a tension, um, which is like 1 over G string times the string length to the p plus 1. If this is some the directions along the brane are some p comma 1, and then there's some directions perpendicular to the brane, which will be r 9 minus p. So, as I say, the objects are heavy. So if the string coupling is weak, then G string is small, and so these objects are much heavier than strings. And so in particular, there are sources for the gravitational field. And so if you study what is the geometry that's sourced in supergravity by the brane, it's all governed by some harmonic function, h of r. So natural harmonic function in the space that's transverse to the branes. So we can look at h of r, which is 1 plus r sub p over r to the 7 minus p. That's a natural harmonic function in 9 minus p directions. Um, and then the particular case that we're going to study is p equals 3. So we have D3 branes. Okay, and so 7 minus p is 4. So this is 1 plus r sub 3 over r to the 4th. And the metric is of the geometry that's sourced by the collection of branes is so it's warped, and it's warped differently in the directions that are along the branes and the directions that are perpendicular to the branes. So in the direction along the brane, we have metric, which is minus dt squared plus dy. So this is some standard Minkowski metric on R31. And there's a warping by a factor of this harmonic function to the minus a half power. And in the directions perpendicular to the brane, there's an inverse warping. So, you can think of this as just like, so what the branes are also sourcing is some gauge field that they're charged under. If I have an object which is p-dimensional, then plus time, the natural object that couples to such a brane is a p plus 1 form. Generalizing the notion of a one-form gauge field couples to a charged particle. And so we just, bump up the spatial dimension. So in addition to this metric, there is a field strength of of some antisymmetric tensor field, which is derivative of H inverse. Then there's dilaton, which in this case, because the 3.1-dimensional Yang-Mills theory is conformally invariant, the dilaton is just constant. Okay, and in string units, this R sub 3 is what? 4 pi alpha prime squared G string n. Okay. So the strength of the gravitational response, of course, is proportional to the number of branes as well as the string coupling. And what else do I want to say? Oh, yes. So the gauge field is being sourced, and then in the geometry, you should think of this gauge field just like any other abelian gauge field. That if you think about what is the energy momentum tensor of a Maxwell gauge field, it exerts pressure in the direction perpendicular to the field lines and tension in the directions along the field lines. And so so what one sees here is that the brane is exerting tension in the direction along the branes and pressure in the direction perpendicular, just like any other abelian gauge field. And so in particular, if I zoom in close to the branes, the harmonic function starts blowing up, which means that this factor starts shrinking. So the proper size of the directions along the brane is getting contracted as I approach the source. and the proper geometry in the direction transverse to the brane is expanding. Okay, so now ordinarily one would think that um, that you should think about the system of the brain coupled to gravity in the way we always think about matter coupled to gravity. That you have the dynamics of the brains themselves, and then you have the dynamics of gravity. And so I think everybody up until Maldacena would have said that you have one dynamical system, and it has two objects in it, namely matter and gravity, and they're coupled to each other, and you need to describe both of them to describe the dynamics. But what Maldacena proposed, which is quite remarkable, is that no, that if we zoom in on the vicinity of the source, we go very close to where the brains are, that you can think of that as a low energy limit, okay? Because in the gravitational response, you have some matter source, and so there's some redshift as you get closer and closer to the matter, and that redshift is blowing up as you get, towards r equals 0. And so the low energy dynamics from the point of view of gravity is to go close to the source. On the other hand, if I'm thinking about, open strings that are describing the fluctuations on the brains, then the low energy limit corresponds to looking at energies which are much lower than the string scale, where the dynamics reduces to the dynamic of the zero mode gauge theory. Okay, and so the big surprise was that there are two distinct realizations of the dynamics of the near horizon dynamics, near source dynamics. One, the near source limit of the geometry. All right, which if we just look at this metric, okay, what does taking the near source limit correspond to? It corresponds to saying, okay, we're interested in going very near the source, so r is going to 0. Um, so um, so we focus on this term in the harmonic function. We can ignore the constant piece. And so the limit is a geometry, which is what? I have a fourth power. So if I take its square root, I get r squared over r3 squared times minus dt squared plus dy squared plus r3 squared over r squared times, and let's write the transfer space, which is 6-dimensional in polar coordinates, d omega 5 squared. Okay. And so this geometry, if we look at this piece of it, this is the geometry of ADS5, and this is the factors of r squared cancel here and here, and so we have. Let me rewrite this as pulling the factor of r squared in with this directions along the brane, plus dr squared over r squared, r3 squared. So that's, as I say, that's the metric of anti-de Sitter space, and then r3 squared d omega 5 squared, the geometry of a round 5 sphere. radius r3 squared, so particular, determined by the where did I write it? I guess I didn't write it. I wrote it earlier. Well, so 3 to the fourth is 4 pi alpha prime squared G string n. Okay. So one has a kind of a curved geometry of constant curvature. Anti-de Sitter space is the space of constant negative curvature with this radius of curvature. And the 5-sphere famously is space of positive constant curvature. Okay, and so on the one hand, one would say that the low energy, infrared dynamics of gravity is supergravity in this space. On the other hand, second possibility is n equals 4 super Yang-Mills in 3 plus 1 dimensions, which is the dynamics on the branes. And the conjecture of Maldacena is these are two dual descriptions of the same physics. Okay. And it's a strong coupling duality. Right? Gravity is strongly coupled when the curvature is large, and gauge theory is strongly coupled when the gauge coupling is large. Okay, so the gauge coupling, G Yang-Mills, is just G string. Okay, so when G string is large, the gauge theory is strongly coupled. On the other hand, when G string is large, the radius of curvature is large, and so gravity is weakly coupled. Okay. Now, if we can rescale everything to make things look a little bit nicer, I prefer to define the radius of curvature to be this scale r sub 3. Let's just call that some length scale L. Okay. And after some rescaling of coordinates, we can write the metric as just this overall scale L squared, and then there's some dimensionless coordinates. Okay, so that's the directions along the branes, and then L squared d omega 5 squared. Well, the directions along the branes plus the radial direction, and then the angular directions transfers to the branes. So this geometry has lots of symmetries. It has clearly an SO6 symmetry of rotations of the 5-sphere. It has 3 plus 1 Poincare symmetry. And it also has a scaling symmetry, where we send t and y goes to some scale factor times t and y. And then simultaneously send r goes to lambda r. Let's say lambda inverse. Okay. Then the rescalings of r and the Poincare coordinates, the Minkowski coordinates, just compensate one another. Dr over r is scale invariant. And so the scale invariance of n equals 4 super Yang-Mills theory on gauge theory description is dual to the scale invariance of this geometry. Okay. Okay. And so in fact, there's a full n equals 4 superconformal symmetry on both sides of the duality. Okay. Now, that leads us to an interesting possibility, which is that n equals 4 super Yang-Mills is an explicitly unitary theory. And, one of our great puzzles in thinking about gravity was, this Hawking paradox, where he questioned whether in the presence of black holes, gravitational physics can remain unitary. And so this duality provides us with a fertile testing ground for this question. If the duality is something that is holding, then we can be assured that if n equals 4 super Yang-Mills theory is a perfectly sensible unitary quantum field theory with it, standard Hilbert space and unitary evolution, then any potential problems with putting a black hole into this geometry have to have a resolution because there is a presentation of the dynamic which is manifestly unitary. So what's the natural black object in ADS5 times S5? Well, it basically consists of taking this metric and dressing it up with the standard lapse function of a black object. So generalize to a black 3 brane. Okay, so collection of n d branes forming a black hole bound state, and that metric looks like the same metric we just wrote. And then we just include the warping of the radial oops, sorry. Okay, where h of r is the standard, well, now here in the appropriate dimension, 1 minus mass over, what would be a harmonic function in 3 plus 1 dimensions becomes harmonic function in 4 plus 1 dimensions, so m over r squared instead of m over r, as one has in the Schwarzschild solution. But otherwise, this is there's a horizon at r squared equals mu. Okay. And so, one is sort of in business. One has a gravity theory, which has some sort of black object with a horizon. And on the other hand, there's a manifestly unitary gauge theory dynamics that describes this. Question? Was there a question? Okay. So, what's the thermodynamics? Well, it's a scale invariant theory. So, thermodynamics more or less follows from scaling. So there's an energy in the system, which is 3 pi, so it's some number of order 1, which we're not going to really care about. N squared, because that's the number of degrees of freedom in n equals 4 super Yang-Mills theory. There's the volume of the spatial manifold that the gauge theory is living on. We call that V sigma. And then T to the 4th. Right, this is a 3-dimensional, let's say T3, just to be right. So we can take the y coordinates and set y to be periodically identified. Okay. And then there's an entropy, a black hole entropy, which again has some coefficient of order 1 that we're not going to really care about, n squared V sigma T cubed, right? So entropy is a number. There are 3 spatial dimensions compensating T cubed. So entropy of order n squared and growing as the temperature grows. And similarly, energy gets 1 part more power of T because it has dimensions of energy. So basically what's happening here is that if we start off at low energies in our Hilbert space and we just start looking at gauge theory excitations, or equivalently in the gravitational side we start populating this space-time with gravitons and other supergravity excitations. Ordinarily, what we would expect to get at low energies is exactly that: a gas of supergravity quanta. Okay, so that would have it's this supergravity in 10 dimensions, and so one would expect the scaling of a massless gas in 10 dimensions. Okay, at some point, and turns out to be an energy of order n squared, you dump enough gravitons into the space, eventually all of that energy collapses and makes a black hole. And so we indeed have the laboratory that we want. Now the and this transition from a gas of gravitons to a black hole is something that goes back to the 1970s. So the transition from a gas of gravitons, supergravitons, at low energies to black holes at high energies is known as the Hawking-Page transition. Some phase transition in the dynamics of gravitational systems. On the other hand, the transition from low energies to high energies in gauge theory, what would we expect at low energy? Well, lower energy, in QCD, the things that rattle around are the mesons, and so the excitations are all UN singlets, and so the same thing is true here. The low energy Hilbert space is populated by multi singlet excitations. In fact, one can come up with a one-to-one map between individual supergravitons and single trace gauge invariant operators in the gauge theory. And so, but at some point, just like in QCD, you raise the temperature enough and you go from some gas of mesons to quark gluon plasma. And so this transition in the gauge theory is the deconfinement transition. So the transition from no black hole to black hole in gravity is dual to deconfinement transition in the gauge theory.
Emil, can I have a clarification?
Yeah.
So the setup we started out with was D3 branes, and the
Yep.
ADS5 which you get is the Poincare patch of ADS5.
Yes.
But there is no Hawking page transition here, right? Because for that you need the global ADS.
Yeah, you're right.
So somehow one makes a logical leap here that you come here and then you go to global and put the Young-Mills theory on an S3.
That's true. I've been sloppy. Well, maybe not so sloppy. There, what morally speaking, what is one interested in? One is interested in parts of the Hilbert space where there's a black hole present, parts of the Hilbert space where there's not a black hole present. And so regardless of whether you're doing the this gauge theory on S3 or on T3, or a little bit later, we're going to consider hyperbolic spaces. There are situations where there's a black hole horizon present, and then there are situations where we just have a gas of gravitons running around in this space. Okay. So I think that's the situation. That's the contrast I want to draw.
That will remain, of course. Yeah.
Okay.
Thank you.
And in fact, I'm really not all that much interested in this low energy regime. My focus in this talk is the black hole regime. And so if the black hole regime starts right away, rather than having a
good
gap,
for you.
that's all the better.
Right.
Okay.
Right.
Okay. Now, so we might like to then study, the formation and evaporation of black holes in this setup. But we face one glaring obstacle in doing so, that in the process, so what one did in taking this limit where one said it's okay to drop the constant in the harmonic function that describes the geometry, is one dropped asymptotically flat space. So if you ask, what this geometry looks like after we've taken the limit, the radial direction is logarithmic, and the angular spheres are constant. Okay, so you replaced flat space. The flat space transfers to the branes, which is indeed asymptotically flat before you took the limit. You replaced it with something which looks more like a cylinder, with some rescaled radial coordinate, which is something more like log r, so that the metric is d rho squared in this rescaled radial coordinate, and then with constant size angular spheres. So the geometry that one is looking at after having taken this scaling limit is something where the space is just some angular S5, and then some radial direction parameterized by rho, which is log r. Okay, so it's some kind of self-similar geometry. The log R is related to the scale invariance of the system, right? That if you rescale the coordinate R, all that's happening is you're doing shifts in rho. Okay, so before taking the scaling limit, what you had was something that looked more like this, right? That this throat at some scale, the scale was governed by this size R3. At that scale, right, at that radial scale, you make a transition in this harmonic function between this being the dominant piece and this being the dominant piece. So there's, before you zoomed in on the region which was way far down this throat, this was your geometry, and so you have asymptotically flat space, and this throat, and then somewhere way down this throat, there may or may not be a black hole horizon. Okay. And, as usual, when there's a black hole horizon, okay, there's some black hole interior, which, might be a fuzzball, might be something else. We don't really know. But we can certainly say of the region outside that there's Hawking radiation. And so what does the Hawking radiation look like? Well, it has some wave function. And that wave function is, if you solve the wave equation in ADS5, the wave functions, here's some horizon scale. The wave functions are all decaying like some power, some r to the minus alpha. Okay. And if you have asymptotically flat space, that's just fine. So you have some wave functions, they're sort of growing, dying as you go away, but they still have some non-zero amplitude when you get out. So if this region is, r of order R3, then fine, the wave function still has some size. And then at that point, you match your solution of the wave equation onto some, outgoing, spherical wave, and the black hole is able to decay. But if you take this decoupling limit where you're going to extend the cylindrical geometry all the way up to the UV scale, essentially taking the process of taking the decoupling limit of this gauge theory is basically one where the entire space-time all the way out to r equals infinity is just this cylindrical throat. And so now you face the problem that this radial decay of Hawking quantum wave functions means that they, the Hawking quanta never escape the system. They're in some bound state wave functions that die to zero as you try to go to spatial infinity. And so while you can form a black hole, naively it looks like you can't make it decay. And since the whole problem with the Hawking, the Hawking information paradox is you watch the black hole decay, and when it's roughly speaking halfway, through its process of decaying, you run into this entanglement problem that Samir described in his lectures earlier this week. The process of creating pairs near the horizon, one of which ends up staying in the black hole and one of which ends up going off to infinity. That going off to infinity is not happening because the black holes are in bound, the Hawking quanta are in bound states, so they all just hang around the black hole and don't go away. And so it's a little bit hard to engineer a situation where after some time you have a bunch of radiation that's far away from the black hole, and you have a problem that the entropy of the black hole that remains can't support the amount of entanglement that it has with the radiation. All the radiation sort of basically when you form the black hole, it emits a few Hawking quanta. They populate some thermal atmosphere near the black hole, and then the system settles down and it's in equilibrium with its thermal atmosphere, rather than having the situation where sort of the tail of the thermal atmosphere is able to leak out to infinity and cause the black hole to decay. So what can we do? Well, one thing that's popular in among string theorists these days is to say, well, let me use this duality to the gauge theory, and so I can ask, how do I introduce and extract energy from the gauge theory? Well, one way of introducing and extracting energy from the gauge theory is to apply operators to the state that you have. And those operators can either, be raising operators that increase the energy or lowering operators that lower the energy. And so let me just act on this, thermal state of the gauge theory by, lowering operators that gradually lower the energy in the gauge theory, and therefore, and in some sense, by hand, extract the energy from the thermal state and make the thermal state decay. And so if you ask, what does that correspond to on the gravity side? It corresponds to making perturbations near the asymptotic boundary, whose effect is to, again, extract energy. So I should have said that there's another sort of Fourier duality going on here as well, that if I have the gauge theory on a torus, okay, and I'm making local operator insertions various places to look at some observable in the Yang-Mills theory, if I ask what is the Fourier spectrum, if this is the description in position space, right? I make an operator insertion. It's some local thing at some point in the manifold that the gauge theory lives on. Okay, and so a local operator is some very UV thing, right? It has so local operators contain arbitrarily high momentum components. Okay, but our whole um, map that we've been constructing between the gauge theory and gravity says that if I want to look at low energy in gravity, low energy corresponds to large redshift, and large redshift corresponds to being somewhere down here near the horizon. High energy, high frequency excitations are things that live in the UV, where the redshift is low, excuse me. Okay, and since the redshift is this factor r squared, if you want to go to high energies, you're going out to large R. And so this process of using local operators to extract energy from the gauge theory is, perturbing the black hole by some very high frequency stuff out near the boundary of space-time. And so that's the thing that people are doing in this game is to try to infer what's going on, down here at the horizon by making local perturbations out at the boundary. And there's lots of room for getting confused about what's going on. In other words, what one is trying to engineer is some map between the gauge theory description and the gravity description, and claim that what's going on in quantum gravity because what's going on in the gauge theory. And so if you made some mistake in that map, then you can get yourself very confused. And, given, all of the things that are being said about exactly, how the Hawking paradox gets resolved in this setup, lots of claims that have been made that are just plain wrong. And I think in large part because people have misconstrued what the map is. And part of the misconstruing of what the map is that you're trying to infer what's going on down here by making perturbations up here. And so it would be much better rather than, if you could engineer something which is much closer to what you want to have happen, which is namely you form a black hole and then you watch it decay all on its own without having to interfere by some perturbations, right? What would be much better if we could just set up an initial state that is some matter that's going to collapse to make a black hole. Watch that matter collapse to make the black hole, and then find some channel by which the black hole can decay, and then just follow the evolution. And so that's the direction that we're headed. Okay. So one thing that we can make use of is that the gauge theory. Oops. So gauge theory, n equals 4, super Yang-Mills on T3 has a Coulomb branch to its configuration space, right? What's the Coulomb branch? It's that so what is n equals 4 super Yang-Mills? It's a gauge potential. It's 6 scalars and 4 myeronothermions, gluinos. Okay. And you should think of these scalars phi as just the things that parameterize where the D3 branes are in their R6. Right, P is 3, so this transfers R6, and so the scalars are just moving these branes around their transfer space. Okay, the gauge fields are the 4 polarizations in the directions along the D3 brane. Okay, and so but if I have 3 plus 1 dimensional gauge theory on either flat space or on a torus, I can give an expectation value to each of these scalars okay. I'm not going to worry about the possibility that that Suma was discussing, where I look at all the non-abelian effects. Let me just assume that all of these scalar fields are mutually diagonalizable. And of course, that will cost me 0 energy. If I look at the commutator squared term in the potential, it vanishes. And so there are flat directions where the vevs of the scalar fields are mutually commuting matrices. And so the phi I, the phi I1 is just the location of of the ith brane. Okay. Now, and so one thing that we can do is to assemble a black hole from collapse of branes on from the Coulomb branch. Okay, so we can at least engineer the first half of what we want, which is an initial state that doesn't have a black hole, by virtue of having some collection of branes that are sufficiently sparse in their distribution that there's no black hole. And then we just make them all collapse to the same point, so towards the origin of the Coulomb branch. Okay, and eventually they'll get dense enough that when they're when they're well separated, if I ask the question, how much energy does it cost me to stretch a W boson between any pair of branes? That energy is proportional to the separation. So when the branes are well separated, the dynamics is U1 to the n because you've spontaneously broken the UN gauge symmetry. Okay, and so well separated. So initial state is well described by U1 to the n super Yang mills. Okay, because we can integrate out the off diagonal degrees of freedom because they're very massive. But then, when the dynamics gets such that the branes are sufficiently compressed, basically it's, in the gravitational description, it's when the branes are forming a gapped surface and an apparent horizon, that all of a sudden, these non-abelian excitations become light. That's when the gauge theory deconfines and you undergo this Hawking-Page transition, very, it's sort of staring you in the face that on the gravitational description, you've collapsed matter and you formed a trapped surface and then eventually a black hole. And in the dual gauge theory, you start off with something where the non-abelian dynamics is Higgsed, and you let it go, into the collapsed phase where as the branes collapse towards one another, you're basically describing a situation where these vevs are time dependent, and eventually you make the vev small enough that you restore the non-abelian symmetry, and you use the kinetic energy of the branes as they approach to make some energy of order n squared, which is the deconfined phase of the gauge theory, which is dual to the black hole. So formation is relatively obvious. Okay. And what's happening in the geometry, maybe we should say what's happening in the geometry, redraw this picture that I had. Is okay, once I've taken this scaling limit where I've decoupled the asymptotically flat region, then I have this cylinder. I have a cylinder, right? And that cylinder goes all the way up to asymptotic infinity. Okay. Now, and then I have some collection of branes. Okay. And so there's some characteristic radius, which is sort of the characteristic scale of the vev of all the scalars. So like the average vev, if you like. Okay. Now, if I erect a Gaussian sphere, the angular sphere, this S5 is the angular direction on this cylindrical geometry. Okay. And a Gaussian sphere, an S5 that's way up here, surrounds all the branes. So that Gaussian sphere is supported by the electric and magnetic flux being emitted by the D3 branes. And so that sphere is prevented from being collapsed by the pressure of the gauge field lines passing through the sphere. Okay. And that's why the that's in some sense why the S5 has fixed size in this throat, is that it's being supported by the magnetic flux that's being emitted by the D3 branes. But if I take that same Gaussian sphere and I start moving it inside my shell of branes, then my Gaussian sphere, they're the three branes that are now, at a larger radius than my shell of branes. And then there are the ones that are still at smaller radius, but they're definitely less than all n of the branes are enclosed within my Gaussian sphere. And so then there is less flux to support the S5. And so the S5 shrinks a little bit until by the time I get to the inner edge of this shell of branes, I sense my Gaussian sphere surrounds no flux. And so the size of the S5 shrinks to 0. So the geometry isn't one where this throat, the throat extends all the way to the UV because the Gaussian sphere up here always surrounds all the branes. But there is no space-time down here below the shell of branes, because what's happened is the S5 got smaller and smaller and smaller until I reach the innermost brane and I have 1 unit of flux and the space-time just pinches off. So the geometry is not something where the space extends infinitely down towards the infrared. The geometry ends at some radial scale, and therefore, since radius and energy are correlated in this throat by scale invariance, there's some energy scale, which is basically, you know, in the gauge theory, there's the scale of the VEV, right? And there are no excitations of the gauge theory below the scale of the VEV, except for some kind of abelian dynamics of the individual separated branes, okay? And so the geometry looks like some kind of capped off geometry in the presence of a bunch of separated abelian D3 branes, okay? But you know, if I'm looking at some time dependent situation where I'm letting those branes, you know, slowly or not so slowly move towards each other, what's happening is that this cap in the geometry as time goes on moves down the throat. And right, so the collapse so you know what's happened is basically you're looking at something which, if this was flat space time, you would say, oh, I have some shell of branes and I'm collapsing it in towards the origin. Okay. And so, you know, a movie of this thing as time goes on is to have the shell of branes get to smaller and smaller radius. Okay. Now you have to put on your logarithmic goggles and say, this is a picture looking down some cylindrical throat. And as the branes get smaller and smaller and smaller radius shells, what they're really doing is, in this warped back reacted geometry, is that they're just further and further down this cylindrical throat. And so the cap in the geometry is just something that's continuing to move down the throat. And eventually, you know, I move far enough down the throat that the dynamics of the branes is highly redshifted due to the back reaction. And then the stretched strings that stretch between the branes, you know, those stretched strings become sufficiently redshifted that they can no longer be consistently decoupled from the dynamics. And at that point, you know, a horizon is forming, because the mantra is that deconfinement in the gauge theory is horizon formation in the gravity. Okay. So, so the collapse process is fairly understandable.
So you're saying that horizon formation in the gauge theory language is the limit when these non-abelian degrees of freedom are getting activated.
Yes. Yes.
Okay.
And now, you know, if I was in a static situation, we kind of know what the geometry looks like. So if, whoops, so if we turn off the collapse, the geometry is governed by the obvious harmonic function. Namely, instead of looking at some harmonic function, which is, after having gotten rid of the constant in the decoupling limit, some R3 to the fourth over R to the fourth, we replace that by a multi-center harmonic function, 1 over n sum of, I equals 1 to n of r3 to the fourth over x minus xi to the fourth, where xi is the location of the ith, xi is the expectation value of the ith component, down the diagonal in this setup. Okay. And so, what's happening is that, if I were to coarse grain this a little bit, it's just like any star, right? You dive in, the harmonic function doesn't blow up. If I have a cloud of charged particles, once I start diving in the cloud, the harmonic function saturates. But the denser and denser I make that cloud, the more and more peaked the harmonic function is. And so, this increasing depth of the throat is coming because, the proper distance here is governed by how big is the peak in the harmonic function. And so, a snapshot looks more or less like that. Okay. Okay.
Can I have another question? So
Yeah.
this departure from this, it's happening because of this velocity dependent potential between the brains?
Yeah,
Because
so
they're
this is
actually,
this is kind of a weak coupling cartoon, and I really have to incorporate the back reaction and do this
I see.
properly, for a moving shell. Once the brains have relative velocity, it's no longer BPS,
Right. Yeah,
and
definitely.
right, and so this harmonic function is no longer protected by standard supersymmetric
Right.
non-normalization theorems.
Right.
Okay. But to the extent that that picture is a valid cartoon, I think what we would say is that there's some kind of Penrose diagram, which is that there's R goes to infinity out here. There's a shell of brains that is collapsing in, and then there's no space time inside the shell. There's just some cap. Okay, and at some point, there's some horizon, some trapped surface that forms. Okay, and if I trusted geometry inside black holes, then I would say, okay, there's it's some kind of black object, and so there's some some nasty thing awaiting me. There's some sort of singularity, which is the black hole singularity. Okay, and so all we have to do now is to engineer the evaporation. Okay, well, if the black holes came in along the Coulomb branch, they can go out along the Coulomb branch. And so I think this is an appropriate time maybe to take a 5-minute break. And when we get back, I'll describe the process of how these brains can re-radiate out along the Coulomb branch and describe an S matrix that's entirely within the purview of this gauge gravity duality. So shall we take a break?
Yeah, we can do that.
Okay.
All right. So are we ready to resume?
Yes, we can I ask a question first?
Yeah, sure.
So you're talking about these individual D branes. There are black D branes already, right? Otherwise, there is no force between them.
I think I can. What I had envisioned was that they themselves are unexcited.
Mm-hmm.
So I want to start with well-separated D branes that are essentially in their ground state. So I have some well-separated abelian gauge theories that are in their ground state. It's n equals 4 super Yang Mills, so there are 256 ground states. But otherwise unexcited, and their entire motion is their center of mass kinetic energy. So I just want to give them enough center of mass kinetic energy that by the time they collapse, they make some black object of some temperature.
But I mean, there's no force between them. Why would they collapse?
I just give them a velocity as an
Oh,
initial
okay.
condition.
Yeah, so
I
it's
see.
I guess in this case it's a velocity square or something. I forgot what in this number of dimensions.
So the
Oh, you mean
initial
the
energy. Uh-huh.
The force, a velocity force.
Okay.
oh yeah, there's right. So there's there's some v to the fourth over
V to the fourth, right?
yeah,
Yeah, by R.
over r to some power. Yeah.
I
And
see.
I'm that back in the days when we were thinking about matrix theory, a rough figure of merit as to when you're starting to form a horizon is when that one loop, v to the fourth over r to whatever, when that interaction becomes of the same order as the kinetic energy.
Right.
There's sort of a virial theorem argument that says that that's the scale at which the horizon forms.
I see. I
So
see.
back when people were thinking about matrix black holes,
Mm-hmm.
and you're in this sort of like low energy regime, you can use the virial theorem and the uncertainty principle to guesstimate, what the horizon size is, and you get roughly the right Schwarzschild value for an 11-dimensional black hole. But here I think we're in a much higher energy regime. That's that matrix theory, old matrix theory story is energies of order 1 over n, and I'm imagining here energies of order n or n squared, in order to make some ADS5 black hole where the natural thermodynamic quantities are all order n squared.
Mm-hmm. I see. So we need to have a sufficiently large initial velocity for.
I think so.
Okay. 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 Thank you.
But to my mind, maybe this is a good place to. By the way, can you still see my
Yeah.
Yes.
my pad?
Yeah.
Okay, good. So what we could ask the question: what is the correct effective field theory for describing this collapse process, right? So let's think about EFT for a minute. Okay. So first of all, the attitude I'm taking is that we're in the strong coupling region, right? So when the gravity is valid, the gauge theory is strongly coupled. So the correct effective field theory is the gravitational one. And so I would say, let's write down an action, which is supergravity, right? So, D10 x, e to the minus 2 phi, root g, r plus 4 grad phi squared minus 12 h squared plus, f squareds of various anisymmetric tensor fields, etc. Right? Okay, that's the supergravity action, and then there's some S brane, which, as I was saying, is just the sum over abelian dBi actions. Tension of the 3 brane, d fork c, e to the minus phi, square root of and this is the pullback to the brane of the bulk geometry, plus the coupling to the 4-form gauge field, right? So that's schematically what's going on, and so the so this again is valid. You know, this is sort of like the abelian approximation in the strong coupling region, right? Is that you know, there's some ambiguities as to what the non-abelian dBi action is, but I don't have to worry about that because all of the stretch strings between the d branes are heavy enough that you can decouple them, and so we should just look at the dBi action coupled to supergravity. And this is a strategy that's been well honed in some analysis I was doing of the 1.5 brane system with postdoc at Tel Aviv, Yoav Zigdan. So this is a similar approach to the F1 NS5P bound states that the Strominger and Waffe counted. Yields all the horizonless, what are called superstrata. Okay. So these horizonless geometries that Benna and Warner, and I've been on some of the papers, and you know, this supergravity crowd that are constructing horizonless, you know, solutions, basically that are kind of like 3-charge versions of the Lunin Matur 2-charge horizonless things. You know, all of those can be thought of as you pull the branes apart a little bit onto the Coulomb branch, and that's the thing that's causing the absence of a horizon. It's exactly the same picture as what I was describing up here, that you cap the geometry off before you get a horizon because the branes are slightly separated. And it's the process of pushing the branes back together that makes the throat get deeper and makes the non-abelian degrees of freedom light enough that you start forming trap surfaces. Okay, so the reason why those geometries are horizonless is precisely that you're slightly onto the Coulomb branch of the gauge dynamics, and so that was sort of the insight in this work. So this is me and Yoav Zigdan. So series of papers that we've written. The most recent ones are there's a 2411 and a 2512. Okay. So the fact that that worked, and it gave us a very nice picture of all of these BPS microstates, and there's just, you know, a whole slew of them, and we were able to sort of match the data of these Coulomb branch solutions to the data you use to construct these horizonless geometries. I should say, this is in a T-dual description. So I'm getting a little bit into the weeds here, but for those of you who know enough about strings and string duality, that maybe this will resonate a little bit. So, you know, in this approach, I have some explicit brane sources. So there are always pole singularities in the harmonic functions corresponding to where the branes are. Okay, but these superstrata are some nice smooth horizonless geometries. So how does that work? Well, one of the dualities that's known in this, you know, lexicon of duality symmetries in string theory is duality between Nuva-Schwarz fibranes and Kaluza-Klein monopoles. That if you do T-duality, you can turn a Nuva-Schwarz fibrane into a Kaluza-Klein monopole. Now, a Nuva-Schwarz fibrane, there's an explicit brane source, but a Kaluza-Klein monopole is just some non-singular supergravity geometry with no apparent, you know, place where you would say there's a brane there. And so so that T-duality is something, T-duality, of course, is a symmetry of string theory. So, you got the same physics in both frames. It's just in one frame, there's obviously a brane sitting there. And in the other frame, it looks like the branes have disappeared into some kind of, monopole flux. So anyway, but going through this exercise of constructing vast arrays of BPS solutions corresponding to separated branes was the sort of thing that started me thinking about, well, okay, can we engineer collapses and Hawking radiation and so on? All right. So okay. So so one way of thinking about this collapse process is to if a reasonable set of approximations, I think, is to say, well, rather than deal with all the complication of the fact that each brane is a point in the transverse geometry, very often what makes sense to do is to make some kind of continuum approximation. So average the location of the brane over the S5. So when you do that, then all that's left in the transverse direction is where that smeared source, it becomes just some radial shell of D3 brane. Okay. And so, you're looking at some, collection of thin shells. And then, in treating what the back reaction of that is on supergravity, you can think of these as some kind of, as I say, matter shells, like, thin shells, and use the thin shell approximation in supergravity and match the geometry using what are called the Israel junction conditions. Anyway, so there's a set of approximations you can use to boil down the dynamics here, including the exact back reaction of the branes, and justify this picture of a collapsing shell of branes. Okay. Now, as I was saying before the break, if the branes came in along the Coulomb branch, they can go out along the Coulomb branch, except that's very hard. Okay. You would like this, hot black hole that you made to be able to re-radiate the branes onto the Coulomb branch, but that's going to be very hard, right? Because in standard flat space Schwarzschild black hole Hawking radiation, the only thing that can get out of the black hole are just the S waves, and only for massless particles, right? Massive particles have a very hard time, being Hawking radiated. It's essentially exponentially compressed. Okay. And so these branes, of course, are very heavy objects, and so they're going to suffer the same issue that how do I radiate a brane? And one way of thinking about that is again from the gauge theory point of view, right? If I have this collection of n D3 branes, and I want to remove one, I have some, here's some kind of thermal state of the gauge theory. And I want to pull one brane back out onto the Coulomb branch. Well, what I have to do is I have to de-excite all of the strings that stretch between the different the n-1 other branes, all of the strings that stretch between the one I'm trying to pull out and all the other ones have to somehow get de-excited for me to go back out onto the Coulomb branch. Otherwise, they're all bound together by the thermal excitations. And so that's going to be a process which is, roughly speaking, exponentially rare in n. So you would expect some kind of emission probability that goes like e to the minus n, because there are n or n-1 branes remaining in the remaining black hole. Okay, so the emission process is going to be extremely rare, but it's the only channel. Right. So as I mentioned earlier, the Hawking quanta are in some bound state wave functions. They can't get out. So they just form some thermal atmosphere in ADS and they just sit there. And we're not going to do anything, we're not going to apply any operators out at infinity that are going to, sample that thermal atmosphere or monkey with the gauge theory in any way. We're just going to set up this state, make this collapse, intermediate state black hole. And then the only channel by which this thing can decay is this exponentially rare process where very, very rarely a single D3 brane goes back out onto the Coulomb branch and starts wandering off to infinity. Okay, but we have all the time in the world. Why not? And just wait for it to happen. And the calculation that justifies it is actually rather pretty, and it really describes any rare process of Hawking evaporation. I think it's actually quite illuminating calculation to go through. So let me describe how it goes. So we can boil everything down to thinking about a charged particle. We can think of the spatial directions, the three spatial directions that the torus that is being wrapped by the D3 brane is not going to play any role in this. So the only role it plays is that the D3 brane is wrapping that direction. Okay, and so the tension of the D3 brane times the volume of the torus is the rest energy of the D3 brane. So it's some mass. So as far as the transverse direction dynamics is going, I should just think of the D3 branes as some point-like massive particles that are trying to, go up this cylindrical throat. Okay, so there's some mass. Well, there's some tension of the D3 brane, and then there's the D fork C. Let me just rewrite the dBi action. Square root of G star minus the gauge field. Okay, and it's rather than the short shell like metric coordinates that I've been writing this black D3 brane geometry in. If you're studying Hawking radiation, you don't want to be working in some kind of singular coordinate system near the horizon, which is what short shell coordinate, right? The DR, oh, let me go back up. The standard Schwarzschild-like coordinates in which we're writing this geometry, have this feature that the warp factor of the radial part of the metric is blowing up, right? So we don't want to be working in some singular coordinates near the horizon. So it makes sense to work in some kind of non-singular coordinates. It's sufficient for this purpose to use what are called Eddington-Finkelstein coordinates, in which the metric looks like some f of r dv squared. My r's and my v's don't look too different. Let me try again. dv squared plus 2 dv dr plus angular stuff. Okay. And as I said, the fact that some torus is being wrapped just contributes the rest mass of this effective particle in the transverse space. Okay. And so in thinking about the dynamics of that, so basically, what you should think about is, there's some radial direction and there's time. And the V coordinate is, if I'm remembering correctly, going this way. Okay. So surfaces of constant R, like this, right? There's some horizon. Okay. And okay. And so, we're trying to understand, what the Hawking process looks like. So the Hawking process is something where, you're going to nucleate a particle-antiparticle pair near the horizon, and one member of the pair runs off to infinity. The other member of the pair, the antiparticle, is stuck in some negative energy state behind the horizon. Okay, so we like to calculate that process. And, that's just some standard particle mechanics in, some kind of point particle action, some kind of S effective, which we can write as, some mass for the particle. We can just think about this world line, okay? And we can introduce a auxiliary world line metric to make the world line dynamics reparametrization invariant. And then there's some, GVV V dot squared plus GVR V dot R dot plus other stuff. And then there's a rest mass term, which I think comes in with a minus sign. Minus E, excuse me. Okay. And so two things to note. One is this metric is only R dependent. So V is what's in mechanics is called a cyclic coordinate. So its conjugate momentum is conserved. So there's some piece of V which is constant, which is, delta S, delta V dot. Okay. And then there's the variation of the action with respect to the world line metric is some world line Hamiltonian, which vanishes by virtue of, reparametrization invariance. And since you're only looking at motion in the RT plane, these are sufficient to basically, control everything. And a consequence of these two features of the dynamics is that, if we go to a Hamiltonian, we, find the conjugate momenta, go to some kind of Hamiltonian version of the dynamics, we'll have a piece of V dot plus piece of R dot, minus, the Lagrange multiplier times the Hamiltonian, and that's it. Okay, so this is 0 by the constraints, and everything boils down to what's sometimes called the reduced action. This is a cyclic coordinate, so the motion in the v direction is just this conserved coordinate times delta v, and then there's some integral of p sub r dr over the trajectory. Now, the thing we're interested in is the part of the trajectory very near where the things are being created, and the particle. How does the particle? It's the Hawking quantum. How does it get out from inside the black hole or the vicinity of the black hole? Okay. And so you could deduce from these two features of the dynamics is that, well, the vanishing, the fact that dv squared has a coefficient, which is some function of r, which in our case is r squared for ADS minus basically the mass of the black hole over r squared. Okay. In particular, though, it's equal to 0 at the horizon. Okay. So there's some zero, that's just the statement that you have a horizon, right? Is that the lapse function vanishes at a surface of infinite redshift, which is the horizon. Okay. And in the process of solving this particle dynamics, you can trace that feature of the geometry to when you make the Legendre transformation to the Hamiltonian formalism, that the radial momentum has a pole. There's a pole which is the this energy, which is the conserved killing momentum, and then there's f prime of r, and then r minus r horizon. Okay. So as I say, this is a direct consequence of the form of the metric, and the fact that you even have a horizon says that the radial momentum has, if the lapse function has a zero corresponding to the existence of a horizon, then the radial momentum has a pole in exactly the same place. Okay. And so if you're calculating the effective action, you have to figure out, okay, if I'm, the trajectory of the particle is going to somehow tunnel, from inside the black hole, and you have my Hawking particle escape. Somehow I have to figure out how to integrate past this pole in the dynamics. And so there's a very, pretty analysis of Per Krauss, Malik Parikh. This is not all the same paper, but a series of papers that these are both Frank Wilczek's students back in the 90s. And so some series of papers that they say, well, okay, very often the way you treat a Hawking radiation is you do some kind of Euclidean continuation, you find some Euclidean instanton, so you're working in imaginary time and blah, 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 blah. The simple thing to do here is just to say, okay, there's this pole. I don't want to, run the integration contour through the pole. So let me just work in the complex R plane. There's some pole here at our horizon. And I'm trying to go from inside the black hole. Well, okay, there's no negative R. I'm trying to go from just inside the horizon to just outside the horizon. Okay. And so how do I do that? Well, the sensible thing to do is just to go around it. So you run the integration contour around the pole, and you choose the way. And so in the process, if you use, this basically is heading in the direction of using the principal value prescription for evaluating this integral. And so in particular, you pick up, so principal value prescription is precisely this business of running the integration contour in the correct side of it in a little semicircle around the pole. And so you pick up a factor of I pi times the residue as the value of the integral of p sub r dr. Okay, plus some real bit. Okay. But we're hunting for a tunneling amplitude. So the tunneling suppression is going to be the imaginary part of the particle action. And so, everything is coming from an infinitesimal vicinity of the horizon. So that's a good thing, right? So that means that the probability for forming these Hawking pairs really only cares about what is the geometry in an infinitesimal neighborhood of the horizon. And so it should be some kind of universal thing that's dictated by the properties of the horizon, and not really caring much about the what's going on, in some, several Schwarzschild radii away. Okay. And so, right. So So here's the pole, okay, and the residue is this. So I pick up the imaginary part of the brane action is minus E over twice the Hawking temperature, because the Hawking temperature arose because this quantity. So I get a factor of pi. Um, and a factor of this F prime of R. And, GR aficionados will recognize this as the surface gravity of the horizon, which in black hole thermodynamics is the temperature. And okay, so everything is controlled then by either a property of the horizon or some conserved momentum of the particle. Okay. And now, of course, whatever the energy is of the escaping Hawking particle is being extracted from the mass of the black hole. So we can use conservation of energy to rewrite this as the change in the mass of the black hole divided by twice the Hawking temperature, and by the first law of black hole thermodynamics, that's just the change in the entropy of the black hole. Now, I was a little bit sloppy here on purpose. Our escaping particle is charged. And so the correct version of black hole thermodynamics, and what actually comes out of a correct treatment of incorporating, it's basically the statement that this conserved momentum, delta S delta V dot, gets the contribution because there's a T dot sitting here secretly in the coupling to the gauge field, and so that enters into the construction of the canonical momenta. And so what you actually find is this minus the charge times the corresponding chemical potential, which is still the correct, using the first law, including all of the things that are being carried away by the D3 brane, gives you the right expression. Okay. Now, okay. And so this is this is a tunneling amplitude, right? What I'm basically doing is I'm computing in some WKB approximation the decay rate, right? It's the decay amplitude. So it's the amplitude squared. Okay. So the amplitude we just computed here, in some WKB amplitude, I have some particle wave function, right? That, I'm looking at some trajectory of this particle, which starts just inside the horizon, ends up somewhat outside the horizon. I'm finding that, so the usual story, the wave function is looking like the classical action, the WKB approximation. And it has an imaginary part. So there's an exponential suppression. Okay, and then I have to square that wave function to get the tunneling probability, and so I get E to the change in the black hole entropy. So S final minus S initial. And this is the end suppression. So right, I start off with, remember I said at the beginning, black hole is some order 1 coefficient. times n squared. So this is the black hole entropy. N squared times the volume of the torus times T cubed, right? And the important thing is this n squared. So I'm looking at some process where I have, I have initially n squared. And then after emitting, so this is, sorry. Yeah, so S initial is going like n squared. S final is going like n minus 1 squared. And the process, the emission process is approximately isothermal. So the delta S, which is S final minus S initial, is n minus 1 squared minus n squared is like 2n. Okay, and that's the exponential suppression. It just reconfirms, the intuition that we started with, that it should be exponentially hard to yank a brane out of this black hole ensemble because I have to simultaneously de-excite all of the non-abelian strings that are binding them all together. Okay. And so I think what's happening here is that gravity doesn't resolve the black hole microstructure, right? It doesn't know anything about it. It just treats the horizon as some smooth thing. So in the gauge theory, it's sort of obvious that what's going on is this, rare, event. It's like, all of the, molecules of air in the room running over to the corner, right? It's, what's the likelihood of all of the stretched strings that are thermally excited and binding these branes together, that, all of the ones that bind one particular brane all de-excite all at the same time and then let it get out. It's that sort of rare process. But okay. And okay. And so this is a somewhat more precise version, put some flesh on that intuition using an actual calculation. Now, I think it's worth also saying a few words as to why why should this tunneling rate be related to the change in the entropy? I think it basically boils down to very basic things that we all believe about quantum mechanics and thermodynamics. In quantum mechanics, what would I say the transition amplitude is? I would say if I want some transition amplitude where I start with some, initial state and I act with some operator like, the evolution operator, some unitary evolution operator, right? And then I make a transition to some final state. Okay, and then the transition amplitude is, the sum over all the final states, matrix elements squared. Okay. Now, if the matrix elements are all constant, are all of the same order of magnitude, so if approximately the same, then this sum over final states is going to be some number times the number of final states. But the number of final states, is e to the entropy times some number. Okay. Now, what should that number be? Well, if we have some thermodynamic system, there's something called the eigenstate thermalization hypothesis that says that any characteristic typical matrix element of any operator you care to look at should be some diagonal piece, and if you're making a transition to a different state, then there's some thing that's like e to the minus s over 2 times some random matrix. With order unit variance. And the only thing then that I need is that for this to work is that the thing that appears here is the entropy of the initial state of the system. Okay. And then, I square this thing, I plug it in, and I get something where indeed all these things are of the same order of magnitude, and I get my e to the SF minus SI. So it seems like it's a reasonable thing that this transition amplitude should be, governed by the change in the entropy of the black hole. And you can also think of it as a kind of a detail balance thing that, when I went through this sketch of the calculation of the WKB amplitude, I said, oh, there's this canonical momentum for the particle trying to get out, and it has this pole at the horizon. Well, the Hamiltonian constraint is quadratic in the momenta, so this is only one of two solutions, which corresponds to the outgoing trajectory. If we look at the ingoing trajectory, it's the other solution to the constraints, and there's no pole. And that just corresponds to the fact that, a particle can sail through the horizon if it's ingoing, and, there's no suppression. It's, option is order one. And, in this language, that just corresponds to the adjoint process. If the thing is unitary, then I should be able to look at the adjoint matrix element, and that just adjoint matrix element just reverses the roles of the initial and the final state. So when I ask how big is this matrix element, when I reverse the role, so this is a process where my initial state is a bigger black hole, and the final state is a smaller black hole plus a Hawking quantum. Okay. If I want the adjoint process is the one where I start off with a smaller black hole and a particle outside the horizon, and I make a transition to a bigger black hole by having the particle fall in. Okay. And, in the estimate of the matrix element, then I just replace the e to the minus s the e to the minus s of the bigger black hole gets replaced by the e to the minus s of the smaller black hole, because I reverse the roles of who was which in the matrix element. And now this becomes an e to the minus sf, and it just cancels the e to the sf in the sum over states. And so, indeed, the adjoint process is order one in accordance with detail balance. And, that's what you see directly from the calculation of the particle amplitude by picking the other branch of the solution of the dynamics. Okay.
Emil, can I ask?
Yeah.
A question. So this picture is very different from particle creation from vacuum. I mean, this is really something which is inside, which is going out, which is
Okay. That's a great question. And it sort of like tees up my conclusion, which is, in this analysis of Krauss, Parikh, and Wilczek, they kind of don't ask where this particle comes from. They just say, what's the likelihood that a particle that's just inside the horizon tunnels out from the black hole? Okay.
Mhm.
Now, okay, so then we ask, okay, what's our model for what's inside the black hole, right? And Hawking's model for what's just inside the horizon is nothing.
Nothing.
Right. So the only way you're going to get a particle near the horizon, to tunnel out, is through some kind of vacuum fluctuation that temporarily nucleates a particle-antiparticle pair, and does this. Right. So indeed, and an antiparticle is just a particle running backwards in time. So you just have some particle trajectory that sort of starts at the future somewhere up here at the singularity and comes back in time and then goes back out. And that's where your particle comes from, just vacuum fluctuations. Okay. Now, if you're Yang Mills person, you would have said, okay, there's some kind of plasma of brains and gluons and crap that fills the interior of the black hole, and so it's not maybe not so unreasonable that just inside the horizon there's lurking some D3 brain that's waiting to get out if just the other brains would let it.
Right.
And so this calculation's like agnostic about which of those two things is going on. And my interpretation of it is simply that, as I was saying, that the gravity calculate, this is a gravity calculation, and gravity isn't resolving the microstructure, and so it can't tell you which of these processes is going on, and the way that it's modeling the actual microstructure is it kind of averages over that, and instead of saying that it's some exponentially rare process of changing the microstate structure to allow the escape of the particle, it just says, I'm going to model that by some kind of tunneling process. I know it's exponentially rare, and I know it has to do with the last stages of the particle escaping from the ensemble of black hole microstates. And so I'll just treat it as some kind of tunneling process that happens near the horizon.
I see.
Okay.
So that means on top of that, you would still have pair creation of D-branes?
Well, so as I say, that that depends on whether you think that there's approximate vacuum structure near the horizon. Okay.
Okay.
And so this brings me to my last point, which is what what is all this? What is the what? How do I square what I've just been showing you with the black hole information problem? Right, just why we're studying this system after all. And so let me first say that there is a Hawking paradox here. If what's going on near the horizon is okay, so here's some horizon, and what's going on is some brain anti-brain pair creation. So okay, so let me contrast two scenarios. So there's the Hawking scenario. The Hawking scenario is that there's brain, anti-brain, okay, and somewhere far in the past, there was this shell of brains that went screaming in and collapsed to make this thing, this black 3 brain. So this is initial collapse. Okay. And so what Hawking would tell you is that what's going on is vacuum pair creation near the horizon, and that after this brain escapes, the thing that's left behind is something where, okay, these brains could be in, their ground states are degenerate, right? Because it's maximal supersymmetry. So there's a 256-fold degenerate ground state of the escaping D3 brain, and so there's some order log of 256. Increase in the entanglement entropy between the black hole and the escaping brain, which is coming from the fact that you basically formed an EPR pair of brains near the horizon and you separated them. Okay. And of course, this is then the what Samir's small corrections theorem is precisely engineered to tell you, is that if this is you're making this black brain evaporate, the entanglement entropy between the radiated branes and the black hole left behind is, monotonically going up. That the delta S entanglement is of order, log 256 for each emission. And the emissions are well separated in time because it's exponentially rare, and so it's just some, one by one, things, entanglement entropy grows, and then you reach a puzzle. So there's a page time. So that, if you draw a graph of the entanglement entropy, it's going up and up and up. But there's some point at which, the point where the S black hole and the S radiation are approximately equal. That's where you can have maximum entanglement, because you have the maximum number of things that this degrees of freedom, qubits or whatever, that are entangled with each other. And then, if you start radiating more branes, then the black hole has less entropy than the radiation, and so the curve has to come down. Okay. And the whole information paradox is the statement that Samir tells you this is what happens forever and ever. And unitarity is the statement that this is what happens. And so how can black hole evaporation be consistent with unitarity? We have that paradox in this framework where everything is dual some unitary gauge theory, and it's Coulomb branch dynamics. And so, of course, the orange curve is the thing that has to happen because the gauge theory dual is some explicitly unitary thing. And I should mention that, you could say, well, okay, so maybe it wasn't this process going on at the horizon. Maybe what's actually happening is that one of these branes that initially fell in is the thing that's actually tunneling out through the horizon. And the problem with that is that, by the time, these branes are starting to be radiated, long ago, these things have collapsed into the singularity, or maybe they're, deposited on some smooth slice in the interior. But, they're well space-like separated from the horizon. And being space-like separated, the part of their trajectory that takes them to the horizon is an additional exponential suppression of the emission amplitude, which is way, way bigger than, that's just to get them to the horizon. Then there's the further suppression that I calculated for you, which is the Hawking radiation suppression. So this process of radiating the original branes to try to restore unitarity is something that's way, way exponentially smaller than the Hawking process. And so it's just not going to happen. And so you're not, according to Hawking, the picture of the late time black hole is some core of N branes, that initially fell in, and then some pool of anti-branes sitting somewhere near the horizon, right? And the gauge theory tells you that's nonsense, right? When you radiate branes onto the Coulomb branch, what's happening here? If you look at some late time, you have these N branes here, and then you nucleated a brane anti-brane pair. So the rank of the gauge theory went up by 2, not down by 1. And the gauge theory tells you that if we put a brane out onto the Coulomb branch, the rank of the gauge theory goes from N to, the rank of the gauge theory, part of the gauge theory is this describing the remaining black hole, goes from rank N to rank N minus 1, not from rank N to rank N plus 1. So, that's saying that, the Hawking picture is almost certainly wrong. And so, there can't be a vacuum. I think the point of the small corrections theorem is telling you there can't be this vacuum structure near the horizon. Otherwise, indeed, as you say, Peiming, then the Hawking process happens if there's some smooth horizon, and you run into this paradox. So therefore, conclusion, the horizon can't be smooth. Can't be, near vacuum structure near the horizon. There has to be some kind of reservoir of branes waiting to be emitted. And that's the fuzzball picture. And so I think I've probably said everything I want to say, except maybe conclude with one caveat, which is that I glossed over um, one aspect of this, which is that the suppression is by the change in the entropy. So if you want to impart to your escaping Hawking brain some radial momentum to take it away from the black hole, the energy you use to give it that momentum detracts from the free energy available to the black hole. And, and since this process is exponentially suppressed, that imparting of extra radial momentum is more exponentially suppressed than the threshold emission of a brane near rest. And so these emitted Hawking quanta are emitted near threshold, and they're only very gradually moving away along the Coulomb branch away from the black hole. And so you might worry that, okay, if I'm spending a long time, marinating in this thermal atmosphere of Hawking quanta, maybe there's some mechanism by which I can transfer, information to the escaping brain before it gets far enough away that it decouples from the vicinity of the black hole, blah, 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 blah. Okay. So if you're worried, if you're not worried about that, then I would say, okay, this toroidally compactified brain setup is, just the ticket. The brains are slowly moving out in something that I like to call the Hohler wind. It's, some, non-relativistic stream of charged particles. It's escaping the black hole. But if it bothers you that that's very slow and there might be some chance for some shenanigans by which the unitarity is restored, we can make that go away by making the Coulomb branch unstable. Right. So
Right.
Sumit, you'll like this. So what we want is some picture like this. Instead of the Coulomb branch being a flat effective potential, we want some kind of unstable effective potential. And the black hole, is sitting up here as a bound state. And then once we emit a brane onto the Coulomb branch, it immediately accelerates to close to the speed of light in short order. Okay. And so how can you do that? Well, if I think about gauge theory dynamics, so I'm compactified on this, three manifold. And I have the standard, trace F squared plus trace d phi squared plus phi commutator phi squared, blah blah blah. But this is a conformally invariant theory, and these scalars then are conformally coupled. So there's an R trace phi squared. Sorry. Conformal coupling. There's a 1/6 here, right? And so for a toroidal spatial manifold, the gauge theory sees a flat potential. For three branes wrapped on a sphere, I see a confining potential. So that's the statement that in global ADS, where the D3 branes are wrapping a sphere, there's some, quadratic confining potential which pushes all the branes into the middle of ADS, and there's no Coulomb branch. But if I wrap the branes on a hyperbolic three-manifold, sort of the three-dimensional version of a higher genus Riemann surface, then there's a term which exactly looks like this, that the branes are unstable. And so the way you form the black hole initially is to send them in with enough kinetic energy that they have enough kinetic energy when, first of all, that they don't bounce off the side of the potential and then escape back out. But then once they do get there, that they can engineer this deconfinement transition, and then you have some long-lived metastable state, which is only slowly decaying by the emission of individual branes. But once those individual branes are emitted, they very quickly run away to spatial infinity because of the instability of the Coulomb branch. So now we really have a situation where very quickly there's a standard effective field theory decoupling, because this escaping brane has a Higgs vev, which tells you that all of the strings that stretch between it and the remaining black hole are getting heavier and heavier and heavier at the speed of light. And so there's some standard field theory decoupling. So there's just absolutely no way after the emission that there's any kind of non-local interaction between the escaping D3 brane and the black hole that's left behind. The kind of non-local interaction that Samir was saying could be a way of bypassing his small corrections theorem is not an option here, because standard rules of decoupling in effective field theory tells you that the only non-local interaction is the W bosons, and the W bosons are forced to sit in their ground state because they get so heavy so quickly that there just isn't anything of that sort. And so I think that coupled with the small corrections theorem is boxing you into this ever shrinking phase space of theory possibilities that there's no non-local interaction, there's no Hawking process, otherwise unitarity is lost. Therefore you can't have vacuum near the horizon. Well, gauge theory kind of tells you that you don't have vacuum near the horizon. You have a plasma ball of branes and gluons. And so that's kind of my picture of what's going on here. It's, I think, trying to put flesh on this idea of the fuzzball as some compact object that's made out of stringy ingredients that is the microstructure of the black hole. And so that's probably a good point to stop and ask if there are any questions.
Thank you. So are there some questions?
Now, a wild question. I mean, could it be that when you first take the n equal to infinity limit, there is no UR-IV decoupling, and there's some funny process which happens in strongly coupled gauge theory?
Yeah, well, it's
or let me put it this way, could it be that what the naive what a lot of people say about wormholes or what have you,
right.
The non-local things in gravity, can I rephrase that in gauge theory, saying that in this limit there must be an UVIR problem?
Yeah, I mean, if you want to invoke some kind of funny non-local interaction at strong coupling, let me make it implausible for you. Let me take gauge theory with a coupling that's 10 to the minus 5. Let me look, at this near BPS situation where I allow the branes to be static, at well-separated locations. Okay, so make their Coulomb vevs, as big as you want. Okay. Then the individual interactions between pairs of D3 branes, it's governed by, some pairwise interaction. So the n of that interaction is 2. Right, so their interaction is governed by a G Yang-Mills that's 10 to the minus 5. So they're all just weakly coupled, pairwise interactions. Now we say, okay, where is there some strong coupling going on? Well, if I go to, you know, energy scales that are enormous relative to the Higgs Vev, okay, well, then what the gravity picture is telling you is that that's governed by, 10 to the 10 branes with a coupling of 10 to the minus 5. So G squared N is, 10 to the 5. So like, yes, there's a geometric picture of infinity in the scalar field space. I don't think we would say in ordinary gauge theory, if I, just take, large n, but very, very tiny G Yang mills, well separated, I've hugely spontaneously broken the gauge theory to U1 to the N.
Right, right. No,
Just because
I
I'm
wouldn't
looking,
believe that either. But
right.
posed this way, it's a falsifiable claim.
So I think that so I think the way I would phrase it is that if you want there to be a non-local interaction, you need there to be some excitation that communicates that interaction, right? You need,
Right.
standard quantum, there needs to be a channel, right? So there needs to be something that does the communication, okay? And what I think what I'm saying is that everything that's described at scales that are way, way, way bigger than the VEV is vacuum physics, right? It's all non-abelian dynamics
Right,
of
right.
stuff that is so energetic that it's in the gauge theory ground state. So there is just no excitation available to do that communicating until you, supply an energy of order much bigger than the VEVs to do that communication. And so, that's the way I would phrase it, and
Yeah,
then what
yeah.
I keep on
So
saying,
I
when
think
I,
in
when I'm
my
saying
language,
it's the
you have
standard rules of
falsified
effective
that
field
claim.
theory,
Yeah.
right? We do this all the time, right? We integrate
Yeah.
out the UV degrees of freedom because they're all unexcited, right? So we
Right.
can ignore them in effective
Right.
field theory. And, you would be saying that, there's lurking somewhere, up in the UV of standard gauge theory, some stuff that, does all kinds of weird things.
Right.
And that's just not the way effective field theory works.
Right.
Okay, other questions?
Yeah, may I ask a question?
Sure.
Yeah. So I was in the first talk of Samir, I asked him about the definition of a fuzzball, and the answer I got was that's not a usual horizon, tender horizon, but yeah. So I'm thinking about referring to my construction. I think can I say I think my construction of the quantum horizon is I think fit the bills of calling it a fuzzball. Can I say that it's like a realized matrix model construction of a fuzzball which has the property that has some property of horizon, which we would like to have, like entropy or
Yeah.
temperature.
So
Yeah.
one of the reasons I went through this digression when I got to the calculation of the emission probability was to emphasize the fact that everything that's going on is really governed by very basic principles of thermodynamics, densities of states, blah blah blah, and that everything is kind of generic. Okay, so you could ask, okay, what makes a horizon in classical GR? It's that stuff, there's like an absorption probability which is order 1, right? You get close enough to the black hole, you fall in, and you don't come back out. Okay. Well, what's the thermodynamic interpretation of that? It's that there's this enormous density of states, far bigger than, like the entropy of a black hole with solar mass is 20 orders of magnitude bigger than the entropy of the sun itself, right? So the black holes are the most entropic objects that we know of in nature. And so it's just standard ergodicity, right? That there's this giant phase space And the way you access it is by falling into the black hole.
Yeah.
And, and so, the reason nothing's coming back out is that it's just ergodically exploring this enormous phase space.
Right.
And as you take H bar to 0, you make that the size of that phase space infinite. So of course it never comes back because it just sits, happily exploring this infinite phase space. But the weird thing about it is that the way you access that phase space is through a finite size portal, right? It's not, from outside, it doesn't look like there's a lot there. It's only when you go inside that you access this enormous phase space. And that's basically this deconfinement property from the string theory perspective. It's perfectly sensible. It's that there is sort of, order n to the 0 degrees of freedom outside and order n squared degrees of freedom, available inside. And so, horizon is basically, I don't know if maybe a better term might be trapped surface, to indicate it's like not inevitable that you can't get out. But there's this trapping phenomenon, which is basically that once you get ensnared by the non-abelian excitations, you have a hard time getting back out.
Yeah.
And so to the extent that your model is dealing with that same sort of physics, that you're engineering some large entropy from matrix structures, then it has the right flavor.
And this,
and I should make one other comment related to this last thing. This the 1+1 dimensional string theory that people used to work on. It was sort of like gauge gravity duality before Maldacena. The earliest example of holography we had was this 1+1 dimensional non-critical string theory, and it had exactly this picture, except it didn't have the black holes at the top of the hill. Right, it had it had strong coupling dynamics that as you get closer and closer to the top of the hill, the string dilaton is getting stronger and stronger. But because all you have are the eigenvalue dynamics of the matrix, the non-abelian degrees of freedom are gauged away. So there's no room for black hole physics because there's no deconfinement. And so basically, what I introduced in getting to this picture was to say, okay, let's find a situation where we have this, this same dynamics and stuff bouncing off potential, but leave room for there being some non-abelian dynamics when you compress the constituents enough.
So the tunneling you described, I'm still thinking could be maybe related to the tunneling of a fuzzy sphere I talk about. So they both give rise to the same kind of WKB amplitude.
Yeah, to the extent you're thinking of this sort of like larger sphere as being some kind of reservoir that you're tunneling things into, that maybe have some of the characteristics that you're looking for.
Yeah.
The other thing I should say along these lines is that I don't think by the time I get to here, I don't think supersymmetry is crucial anymore.
Right.
Right. When I put the gauge theory on a hyperbolic manifold, it's like it is just like looking at conformal field theory on a higher genus Riemann surface. There's no global supersymmetry, so BPS etc. is out the window. So we might as well just study some matrix model. Forget about supersymmetry and whether there's a flat. There is no flat potential, so we're not trying to engineer a flat potential anymore. So let's just find the simplest model we can that has the non-abelian dynamics we're interested in studying.
Yeah.
And so things like the model you were describing, where you say, okay, let me just have a few matrices and not really bother much with the fermions or just not
supersymmetry.
Not care so much about supersymmetry, because supersymmetry is not playing a crucial role here. The thing that's crucial here is the non-abelian deconfinement.
Right. Maybe there's a embedding in string theory, and the master maybe come from some Maya coupling or something.
Yeah. It's nearly 12:30, so I guess we should stop here. Because we can't we meet in person, so we are canceling the discussion session in the afternoon. So let's thank Emil again, and also thank all
Okay.
the speakers and participants for your active participation.
And the
Hope
organizer.
And
and thank
let's
the
thank
supporting
all the
staff.
organizers for this very stimulating workshop.
Yeah.
Yes, thank you very
Okay.
much. So the lectures will be available on YouTube channels.
Okay.
I'll send everyone the link later. So thank
And
you all very much,
Thank
and
you.
hope to see you guys soon.